Okay, let's dive into this. From the tiniest little bacteria all the way up to us with our huge, sprawling cities, every single population on Earth is basically playing by the same set of rules. It's this constant push and pull, right? A real balancing act that decides who thrives, who just gets by, and who, well, disappears. So today, we're going to unpack the science behind that whole game. It's called population dynamics.
So let's kick things off with a little puzzle. Think about this. A single bacterium, if you give it everything it wants, can multiply into billions in just a few hours. So why aren't we swimming in bacteria right now? I mean, why isn't the whole world just covered in them? What's stopping them? Answering that question, well, that's the key to everything we're going to talk about.
And the thing is, the answer isn't just random chance. Nope, it follows this surprisingly predictable pattern. You can almost think of it like a simple math equation, You got inputs that make the numbers go up and outputs that make them go down. And this basic formula, it applies to literally every living thing on the planet.
This whole field of study has a name, of course. It's called population dynamics. And look, it's way more than just counting animals or people. It's all about digging into the why, What are the real forces that cause these numbers to go up and down over time?
So this whole process really boils down to just four main things. It's actually pretty simple. Imagine a small town, right? The town gets bigger when more babies are born than people pass away. That's birth rate versus death rate. And of course, if people move in, that's immigration, the population grows. But if the main factory closes and people have to move out for work, that's emigration, the town shrinks. This same exact logic works for everything. I mean, everything. A herd of elephants, a colony of ants, you name it.
Okay, so when you start tracking these numbers over time, you see these two totally different patterns pop up. First, there's how a population could grow if it lived in a perfect world, with no limits whatsoever. And then there's how they actually grow, here in the real world, where things are a lot tougher. Let's take a look at the story these two different curves have to tell.
All right, first up is the dream scenario. This is called exponential growth. This is exactly what happens with our bacteria friends in a lab where they have all the food and space they could ever want. The population doesn't just add numbers, it multiplies, it accelerates. More individuals mean way more births, and the population just skyrockets. It creates this really distinct J-shaped curve you can see here.
But we all know nature isn't some perfect laboratory, right? Out here in the real world, things like food, water, and even just space to live, they're all limited. So what happens is, after that first big burst of growth, things inevitably start to slow down. The population starts to bump up against those limits, and that growth curve, it flattens out, making this much more realistic S-shaped curve. Putting them side by side like this really drives the point home. That J-curve, it's a fantasy, right? It's this idea of endless, unchecked growth that's just not sustainable in the long run. But the S-curve, that tells the real story. It's a story of limits, of challenges, and eventually of finding a balance. It's the pattern of life that we see pretty much everywhere we look.
So what exactly causes that S-curve to level off like that? It's not just a coincidence, not at all. It's a really basic rule of ecology. See, every single environment has a hard limit. Think of it like a maximum occupancy sign.
And that limit has a name: carrying capacity. It really is like nature's max occupancy sign for a building. It's the biggest population size of one species that an environment can handle day in and day out, without the whole system falling apart.
So what decides that number? Well, it's a whole mix of essential things. Take a forest, for example. It only has so much food, so much water, and so much space for deer to live. If the deer population explodes, pretty soon there's not enough to go around. The environment just can't support them all. That is carrying capacity in action, right there.
Now, this carrying capacity doesn't just magically appear. It works through these specific pressures, things that are actively pushing back against the population getting any bigger. And these pressures are what we call limiting factors.
And these limiting factors basically come in two flavors. First, you've got your density-dependent factors. These are the problems that get way worse as a place gets more crowded. Think about it. The more animals you pack into one area, the tougher the competition for food gets, right? And diseases, they can spread like wildfire. Then, on the flip side, you have density-independent factors. These are the things that don't care how big or small the population is. A massive flood or a forest fire, it's going to cause problems whether there are 10 deer or 1,000. And impacts them all just the same. So why should we care about all this? Well, here's the kicker. These rules, they don't just apply to bacteria in a lab or deer in a forest. They apply to us too. And understanding them isn't just an academic exercise, it's absolutely crucial for figuring out our own future on this planet.
I mean, for a long time now, human ingenuity has been amazing at pushing back against nature's limits. Thanks to incredible advances in medicine, farming, and technology, our population has just exploded. We've basically been living on a J-curve of growth, unlike anything this planet has ever seen before.
But here's the thing. The laws of nature haven't gone away. They still apply. And when any species overshoots its carrying capacity, the consequences can be, well, pretty severe. For us, that means running the risk of using up our natural resources, creating way too much pollution, and making climate change even worse. And these aren't just some far-off, abstract ideas. They are the direct results of all of this population pressure.
But the good news is we understand these rules now. This science isn't just about doom and gloom, it's a toolkit. It's something we can actually use. We use it for things like wildlife management, to help protect endangered animals. We use it in farming to make sure we don't overgraze the land. We even use it in urban planning, trying to build cities that can actually last without wrecking the environment around them.
And all of this really leaves us with one final huge question. We know the Earth has its limits. That's a fact. But we also know that human innovation has managed to stretch those limits again and again. So as we look ahead, the real question isn't just if we can keep going, but how we do it. And maybe even more importantly, for how long.